World population has been on the rise for the past century and continues to do so. With the increase in numbers, the demand on products increases as well. This increase in demand forced factories and producers to find means of enhancing, enlarging, and fastening the product production rate using any means necessary, and especially the advancement of technology. Technology, however, can be a double-edged sword. Even though modern technology has increased work safety significantly, work hazards are still present and fatal accidents still occur. Factory accident rates are rising. There are almost 3 deaths and 47 injuries reported every day on average. According to Eurostat, an average of 2 fatal accidents occur per year, and this statistic was mostly on subjects from first world countries. Not only that, but studies have shown that the average cost implicated by an industrial accident is above $30,000. Be as it may, the number of major industrial accidents is in a decrease. This is due primarily to the use of automation and the integration of robotics in most industries. While the aim towards the use of robots is to increase work rate, amplify efficiency, and reduce the risk on workers, human-robot collaboration is yet to reach a point to nullify work-related accidents. Locations such as nuclear power plants, ceramic factories, and vehicle painting booths impose a significant safety and health issue for any operator in their work area. Situations like these guide our proposed solution towards a certain criterion, a criterion in which operations performed over a distance is necessary. Our solution to the problem revolves around the use of teleoperation alongside virtual reality to place the operators in a safe simulated work environment. Additionally, AI will be used as to implement the self-aware technique on controlled robots. The integration of tele-operated control through virtual reality with AI may lead to an increase in human-robot collaboration significantly.
Our proposed solution can be applied on different types and sizes of robots. The system depends on new technologies, and more importantly, it guarantees safety for workers, and it's easy to use as its operation requires no intense experience. Hence, it aims to increase functionality and productivity of industrial workplaces. This makes our solution simple and applicable in different work fields. Our solution is demonstrated on a customized 7 degrees of freedom serial robotic arm. The robot model resembles robotic arms operating in different industrial fields, doing tasks like welding and assembling. The robot, in our case, consists of 6 revolute joints mounted on a prismatic joint, all actuated by stepper motors to increase the workspace of the whole arm and to imitate pick-and-place tasks.
To apply the solution, 2 platforms were used, Unity 3D and ROS. Unity 3D is a free-to-use game engine. Unity was selected due to its strong physics simulation abilities, ease of use, and ease of VR accessibility. Moreover, Unity gives the ability to build a custom environment, thus giving a very flexible user interface. On the other hand, ROS, or Robot Operating System, is an open source middleware specifically customized for working with all different kinds of robots. ROS is used because it allows for the communication between different software, all the while giving functional implementations to the system.
In order to visualize the robot in ROS platform, the model is imported in RViz visualization tool. From there, motion planning and execution of any desired positions can be carried out. In the meantime, the trajectory motion is displayed on a simulated real-world environment using Gazebo Dynamic 3D engine. Finally, the data of the joint angles and positions are easily monitored and can be transferred to other connected ROS nodes for further calculations.
Differing from ROS, Unity being a game engine makes the whole software a strong visualization tool. The main aspect of visualization in Unity is the created environment. The environment in Unity is called the scene. The scene is highly adjustable and easily changed, giving a very flexible user interface and diversifies the user experience. To have convincing physical behavior, Unity's built-in physics engines provide components that handle the physical simulation. With just a few parameter settings, we can create objects that behave passively in a realistic way. Unity gives us the power to create truly immersive, cutting-edge AR and VR applications. The headset used is the Oculus Rift S. It was preferred over other headsets due to its easy setup and flexible inside-out tracking. To be able to use the full power of VR integration, VR Toolkit is introduced. VRTK is an open source package that provides the ability to interact and move in the environment, giving us a much easier way to implement our solutions.
Now that our two main platforms, Unity 3D and ROS, are set up, we need to be able to communicate between them. To tackle this objective, ROS Sharp is used. ROS Sharp is a set of open source libraries written using C# scripts to enable communication between platforms such as Unity with ROS using WebSocket communication protocol. Using a URDF parser supplied by ROS Sharp, the model is imported from ROS to Unity. C# scripts in Unity are used to send the required end position of the robotic arm to ROS for calculations to occur. The inverse kinematics for the required position is solved, then the angles acquired of each joint are sent back to Unity by using ROS Sharp supplied libraries. The joint angles are then transmitted towards the hardware. To demonstrate the system, the user grabs the sphere representing the required goal position. When the user lets go of the sphere, the values of the position and orientation are sent to ROS via ROS Bridge, a ROS Sharp library. Inverse kinematics are solved for the position, and then the acquired motion is executed on Orvis. The motion executed on Orvis is then transferred to Unity. Unity then performs the same motion but takes into consideration physical attributes of the robot and the environment.
Our project, we are using artificial intelligence to control our robotic arm and make it smarter, as an AI solution will lead to an increased control, resilience, quality, and time reduction. Our aim here is to enable the robotic arm we are working on to create a self-image to itself, so that it can do three important and crucial tasks: adapting to different situations, handling new tasks, and finally detecting and adapting to physical damage or mechanical issues. But how can the robot become self-aware? Let's take this example from engineers at Columbia University in New York, who used the process of self-simulation to give a 4 degrees of freedom robotic arm the ability to imagine itself. Via trial and error, the robot babbles, collecting action sensation pairs and abstracting a model. Visualizing that model, different tasks like writing can be performed. Not only that, but also it will detect any deformations that occurs in its body and adapt a new model on the change. This self-aware technique is something that we are striving for with our 7 degrees of freedom manipulator, to be able to adapt to any damage or change in the surrounding environment with zero prior knowledge of physics, geometry, or motor dynamics. Therefore, we focused on developing and creating much simpler AI systems like simple neural network.
The goal of the deep neural network in our problem is to predict the joint's angles that will lead to achieve the desired pose of the end effector without any mathematical calculations. This problem is known as the inverse kinematics problem, and it is one of the main challenges in robotics control. In this stage, we have collected our training data from the simulation, but later the data will be collected from the hardware. In order to do that, we generated the workspace using forward kinematics. And by doing so, we were able to generate 680,000 training samples. Each one consists of positions x, y, z and the orientation theta, phi, psi of the end effector with respect to the home position. Afterwards, we built our first deep neural network architecture, and then we performed the training process and noted the results. The accuracy of the first architecture was 53%, and then we optimized many parameters like number of layers, number of neurons, and learning rate. After doing these optimization procedures, the accuracy of the neural network reached 92.6%. In order to visualize what 92.6% accuracy means, we fed a path of 4 points to the deep neural network to see the output of the desired path and the actual generated path. Even though the accuracy is 92.6%, deviation from the goal path is still relatively high. To conclude, this error can be acceptable in several classification problems, but in our case, the regression problem, it is not good enough and we are currently working to improve it.
With hazards and danger present in many work fields, some of which are considered life-threatening, such as work in nuclear power plants, technology is looked at for a solution. We provide a solution by integrating new and rising elements such as VR and implementing young methods like AI techniques into the system, with the inclusion of teleoperation, all the while meshing them with free software like Unity and Rust, each on a separate operating platform to further advance human-robot collaboration.
The platforms provided give the ability to push the developed scene to distinct operating platforms such as Linux, iOS, and Android. The platforms aids developers by giving the ability to launch and track the product. Another way Unity assists the product in is by allowing for user feedback. User feedback can be very helpful for gathering information regarding system requirements and provides insight into risk and ways of mitigating them.
The suggested solution can be employed in any field that utilizes robots in any sense of the way. We predict that our solution can have the main impact on two fronts, social and economical. Social, as the world development need to create robot-human teams to cooperate in areas that need human expertise and influential robots. From an industrial perspective, with several robot companies moving into the field of VR, this solution will accelerate the work on the integration of the implemented areas together, while also boosting the VR field, with the VR market is valued at $6.3 billion as of 2018 and expected to reach $120 billion by 2026. VR will reduce training costs and time for the workers on robots, as they can be trained on virtual robots, not on real ones. Also, self-aware AI technique in the robot will decrease the maintenance costs of the robot, as it can compensate its mistakes for actuators or mechanical inconsistencies.
As we push the limits of human-robot collaboration, our proposed project makes no place beyond reach and no environment dangerous. This can be perceived as a small step in the name of progress, but a giant leap towards innovation.